Welcome back, deep divers. Sometimes a question pops up and it just grabs you. And for today's deep dive, it's all thanks to you. So many of you wanted to understand black holes better.
Yeah, it's no surprise, really. Black holes are these incredibly fascinating objects in the universe, right?
Totally. And to really get our heads around them, we've got this awesome stack of sources, articles from astronomy.com, some mind-bending stuff from Big Think. Oh, and we've even got a clip from the Joe Rogan Experience with Brian Cox, the physicist. You know him, right?
Oh, yeah, Brian Cox is great. And we also have a piece from BBC Earth. And for a really deep dive into time dilation, we've got insights from profound physics. We're going to try to extract the core knowledge about these cosmic giants.
Exactly. And I think a question that a lot of people have is, could you actually survive falling into a black hole?
That's the big one, isn't it? And I think what we'll find is the answer is not a simple yes or no. It's kind of an intriguing, it depends.
It depends. Okay, well, let's start with the basics then. What kinds of black holes are out there? Because it's not just like one type of cosmic vacuum cleaner, is it?
No, not at all. Our sources outline several distinct categories. We have stellar mass black holes. BBC Earth and astronomy.com both explain that these are what's left after really massive stars collapse. It's like the dense core that's left behind when a star goes supernova.
Right. So it's like the stellar heavyweights that couldn't hold themselves together. And then, of course, there are the really huge ones, the supermassive black holes.
Yeah, these are the behemoths. Astronomy.com and BBC Earth, they both talk about these. They say these are found at the centers of most galaxies, and they have these incredible masses, like millions or even billions of times the mass of our sun. And, Sagittarius A star, the one at the heart of our own Milky Way, that's a great example. And the JRE clip, they talk about the black hole in M87, which is this just monstrous one, to illustrate, the scale we're talking about.
Billions of solar masses. That's almost impossible to really get your head around, the scale of that. So you got those two, the stellar mass and the supermassive. What other kinds of black holes are there?
Well, astronomy.com and BBC Earth also point out that there are intermediate mass black holes, as the name suggests. They fall somewhere between the stellar and the supermassive ones in terms of size. So, somewhere between about 100 and 100,000 solar masses.
Okay, so kind of in between category. And then there are these really interesting ones, the primordial black holes.
Ah, yes. Astronomy.com mentions these. These are theoretical, thought to have formed very early in the universe, like shortly after the Big Bang. And what's fascinating is they could be incredibly small, some of them potentially as small as an atom.
An atom-sized black hole. Wow. Okay, so the idea of these objects, it's really evolved over time, hasn't it? I mean, do our sources talk about the initial kind of concepts?
Yeah, they do. It's really interesting to trace the history of these ideas. Astronomy.com reminds us that the concept of objects so dense that not even light can escape, well, that idea dates back to 1783. John Mitchell, he called them dark stars.
Dark stars, that's a great name. And of course, it took a while for, that to be confirmed. The bet between Stephen Hawking and Kip Thorne, that's a really good example of the scientific process in action, isn't it?
Oh, absolutely. Astronomy.com tells us about their famous bet in 1974 about Cygnus X1. Hawking, he bet against it being a black hole, and Thorne argued for it. And, it shows how even the greatest minds in the field can have different interpretations. And it was only in 1990 that the evidence really confirmed Cygnus X1 as a black hole. Thorne won that one.
Right. So the 90s were kind of a key time for black hole research, it sounds like.
They were. Astronomy.com points out that there was a real explosion of black hole discoveries in the 90s. And it became clear that these weren't just, rare, exotic objects, but they were actually fundamental to the universe. There are probably millions of stellar black holes in our galaxy alone.
Millions. Wow. Well, that brings us to, how black holes are portrayed in popular culture. Sci-fi loves to use black holes for all kinds of things, travel, wormholes, all sorts of crazy ideas. But our sources, they seem to want to ground us in the reality of the physics and the fact that most of that is probably not going to happen.
Exactly. The idea of black holes as gateways, for interstellar travel, it's very appealing. But astronomy.com, they rightly point out that the reality is likely to be far less hospitable. And the idea of surviving a trip through a black hole, as we understand physics today, is pretty naive.
Okay, so let's get into those realities, the science of black holes. The first big thing is the event horizon. What is it exactly?
The event horizon and Big Think, astronomy.com, and BBC Earth, they all define this. It's basically the point of no return. It's the boundary around a black hole where gravity gets so strong that nothing, not even light, can escape. Once you cross it, you're trapped.
And this is where the size of the black hole really matters, doesn't it?
It does. Astronomy.com and BBC Earth both make this point very clearly. If you were to fall into a stellar mass black hole, crossing that event horizon would be, well, it would be the end. The tidal forces, the difference in gravity between, say, your head and your feet would be immense.
Right, right. And that leads to, what they call spaghettification.
Yeah, exactly. BBC Earth uses that term, and Astronomy.com explains what that means. You'd be stretched, literally stretched, into a long, thin stream of particles. It wouldn't be pleasant.
Not at all. But what about the supermassive black holes? I remember Brian Cox in the clip saying that you might not even notice crossing the event horizon of one of those.
That's a really interesting point he makes, and Astronomy.com and BBC Earth echo that. Because these black holes are so vast, the tidal forces at their event horizons can actually be relatively weak. So theoretically, you could cross the event horizon of a supermassive black hole and not feel any immediate effects. Like Brian Cox says, it might feel like just passing through empty space.
Wow. But that doesn't mean you'd be safe, though, right?
No, not at all. Because at the center of every black hole, there's the singularity. Big Think, Astronomy.com, BBC Earth, they all describe it as a point of infinite density, where all the mass of the black hole is concentrated. Our current understanding of physics just breaks down at the singularity.
So even if you don't get spaghettified at the horizon, the singularity is the ultimate end, right?
Yeah, it's game over at the singularity. And Astronomy.com emphasizes that once you're past the event horizon, all paths lead to the singularity. Brian Cox and Big Thing also say that, reaching the singularity could very well be the end of time, according to Einstein's theory.
The end time. That's a really, really heavy concept to think about. Now, Big Think mentioned some other bizarre stuff, like space and time reversing roles inside a black hole. That sounds crazy.
It does, doesn't it? The theory is that once you're inside the event horizon, space and time kind of flip. Moving towards the center of the black hole becomes like moving forward in time, according to Big Think. Brian Cox also talks about this idea.
So the singularity isn't just a place in space, it's a point in the future you can't avoid.
That's wild. Are there any other weird phenomena around black holes? Like, I think Big Think mentioned something called the photon sphere.
Ah, yes, the photon sphere. Big Think describes it as this region around a black hole, about 1.5 times the Schwarzschild radius, where gravity is so strong that light itself can orbit the black hole.
Wait, so does that mean, like, you could theoretically see the back of your own head?
Exactly, because light from the back of your head could travel around the black hole and come back to your eyes. It's a really cool illustration of how much black holes distort space-time. It's kind of a funny image, seeing the back of your own head when you're talking about something so powerful. Okay, so what about if you're watching someone else fall into a black hole? What would you see?
Well, both Big Think and Profound Physics explain that from the outside, you'd see the person falling in start to slow down as they approach the event horizon. And their light would get shifted towards the red end of the spectrum because of the intense gravity. And eventually they would just seem to freeze and fade away at the event horizon.
So it would look like they just stopped right at the edge, like your time stopped. And that brings us to time dilation, which Profound Physics goes into detail about. This isn't just science fiction, right? It's a real thing.
Oh, it's very real. Gravitational time dilation, as Profound Physics tells us, is this phenomenon where time actually runs at different rates depending on the strength of the gravitational field.
Oh.
Near a black hole with its immense gravity, time slows down significantly compared to time far away from the black hole.
Profound Physics talks about a geometric explanation for this. Something about basis vectors in the time direction getting shorter closer to the black hole. Can you unpack that a little?
Sure. Imagine, a ruler. The markings on the ruler are like those basis vectors. And closer to the black hole, those markings would get closer together. It means that a unit of time near the black hole is a much smaller piece of time compared to a unit of time far away.
So like a second near a black hole would be a tiny fraction of a second here on Earth.
Kind of, yeah. Profound Physics talks about the Schwarzschild radius, which is a way to measure the size of a black hole's event horizon. It's related to the black hole's mass. And they also talk about the Schwarzschild metric, which is this mathematical description of space-time around a black hole.
And Big Think and the JRE clip give some examples of the Schwarzschild radius. For the sun, it's only about 3 kilometers. But for the Earth, it's less than a centimeter. That's amazing.
It is. Profound physics makes it clear that a black hole is any object whose Schwarzschild radius is larger than its physical radius. That's what makes them so dense and creates this immense gravity.
Right, right. And profound physics makes a distinction between coordinate time and proper time. Can you explain that?
Sure, coordinate time is like time as measured by a distant observer. Proper time is the time experienced by someone who's actually in the strong gravitational field. So for the person falling into the black hole, their own experience of time would feel normal to them, even though to someone far away, it would seem like their time was slowing down.
Okay, I get it. So when we say time stops at the event horizon, we're talking about coordinate time, not proper time.
Exactly. Profound physics emphasizes that for the person falling in, they wouldn't notice anything special about time at the moment they cross the event horizon. But of course, their experience and their ultimate fate would be very different from what a distant observer would see.
Profound physics also gives us the formula for the time dilation factor and some pretty mind-blowing examples of how much time can slow down.
Yes, and those examples are really interesting. They show that even just outside the event horizon, the time differences are huge. At a distance of 1.00005 times the Schwarzschild radius, for instance, a year for the person near the black hole would be equivalent to 141 years on Earth.
141 years. Wow, that's a huge difference. Profound physics also mentions that if a black hole is rotating, it makes things even more complicated. There's something called frame dragging, right?
Right. The simplest black holes are non-rotating and uncharged, but real black holes can rotate, and those are called Kerr black holes. And there's the theoretical possibility of charged black holes, too, called Reisner-Nordström black holes. And if they're both rotating and charged, they're Kerr-Newman black holes. And these properties affect the space-time geometry around the black hole, and that affects things like time dilation and this frame dragging effect.
Okay, so we can't directly see black holes because light can't escape them. How do we even know they're there then?
Well, BBC Earth and the JRE clip both talk about how we detect black holes indirectly. One way is by looking at the effects they have on the matter around them. When stuff like gas, dust, even stars gets pulled into a black hole, it often forms an accretion disk. That's a swirling disk of superheated material that emits a lot of radiation.
And that radiation is what we can detect. Is that what we're seeing in those images of black holes, like the one of M87 that Brian Cox showed us?
Exactly. That image of M87, which was captured by the Event Horizon Telescope, it's not actually showing us the black hole itself because the region inside the Event Horizon is truly black. What we're seeing is the shadow of the black hole against the bright background of the accretion disk.
Right, right. And there are also gravitational waves, right, which Brian Cox describes as, quote, storms in time, which is a phrase that Kip Thorne uses.
Yeah, gravitational waves are another way to indirectly detect black holes, especially when they collide. And the Laser Interferometer Gravitational Wave Observatory, or LIGO, as the JRE clip and BBC Earth explain, is able to detect these waves.
So we can see black holes, even though they're invisible, by looking at the effects they have on their surroundings and on space-time itself. That's pretty amazing. Now, one of the biggest mysteries about black holes is this thing called the information paradox. Brian Cox talks about it in the JRE clip. What is that exactly?
It's a really fascinating problem. The black hole information paradox comes from this conflict between two of our best theories in physics. We have Einstein's theory of general relativity, which describes gravity, and we have quantum mechanics, which describes how matter and energy behave at the smallest scales. And general relativity seems to say that when something falls into a black hole, all the information about it is lost. But quantum mechanics says that information can't be destroyed.
So, like, if I threw a book into a black hole, according to general relativity, all the words in that book would be gone forever.
Yeah, that's the implication. But then in the 1970s, Stephen Hawking came along, and he did this amazing calculation that showed that black holes aren't completely black. They emit a faint radiation called Hawking radiation. And that means black holes actually have a temperature, and over a very, very long time, they can evaporate.
But if black holes evaporate, what happens to all the stuff that fell into them? Does the information come back out somehow?
That's the paradox. The original idea of Hawking radiation was that it was just random thermal radiation. It didn't carry any information about what had fallen into the black hole, so it seemed like all that information was just gone.
So physicists are still trying to figure out how information might be preserved, maybe in the Hawking radiation somehow, or somewhere else.
Exactly. It's one of the biggest puzzles in physics today. Solving it could change our understanding of reality in a big way.
Now, BBC Earth and Astronomy.com also mention these more speculative ideas about black holes, like wormholes and white holes. Those sound pretty wild.
They do, don't they? Wormholes are these theoretical tunnels in space-time that could connect distant parts of the universe. And white holes are kind of the opposite of black holes. They're theoretical objects that would spit out matter and energy instead of sucking it in.
So, like, could you travel through a wormhole or escape from a black hole through a white hole?
Well, that's the science fiction idea, isn't it? But both Astronomy.com and BBC Earth stress that these are highly theoretical concepts. We don't have any evidence that they actually exist. And even if they did, Stephen Hawking suggested that trying to create a stable wormhole for time travel would probably be impossible.
Okay, so back to our original question. Could you survive falling into a black hole? It really does depend, doesn't it?
It does. For a stellar mass black hole, the answer is a pretty clear no. You'd be spaghettified by the tidal forces. But for a supermassive black hole, you might cross the event horizon without any immediate problems. But eventually, you'd reach the singularity. And that's where things get really, well, really weird.
So those science fiction movies where people just fly through black holes, that's not how it works at all.
Not even close. The reality as we understand it is much more extreme and inescapable.
Okay, well, this has been a really mind-blowing deep dive into black holes. Let's sum up what we've learned.
We've talked about the different types of black holes, the event horizon, the singularity, time dilation, how we observe black holes, the information paradox, and even these theoretical ideas about wormholes and white holes.
And it really makes you think, doesn't it? About the limits of our understanding of the universe. If black holes can warp space-time so much, what other strange things might be out there that we haven't even imagined yet? That's something for everyone to ponder. Thanks for diving deep with us.